All right. So to explain the lift on the airfoil, we will be looking at basically what causes the pressure to decrease on various part of the airfoil, right? And to start the analysis, we are going to be looking at, first of all, an equation that describes the conservation of mass. The conservation of mass equation is going to give us more or less the distribution of velocity in the flow field. And the distribution of velocity then feeds into the conservation of momentum. So that is Newton's second law, F equal to ma, right? So F equal to ma really generalizes in the fluid dynamics context through some mathematical transformation into the conservation of momentum. If we know the velocity field and we have the conservation of momentum, then we know what the pressure distribution is in the flow field. So let's start the analysis by looking at the physics and mathematics of mass conservation. To start looking at mass conservation, we always need to draw a control volume. So let's just focus on this picture here and draw a control volume that is a square of length delta x equal to delta y. Okay, so let's assume delta x is equal to delta y. And let's look at how does mass within this control volume. And by the way, this control volume is fixed in space and the control volume does not move with the fluid. If you have read the reading assignments in advance, you're gonna know that this kind of control volume has a name called Eulerian control volume. So this is Eulerian control volume. Right, that means the control volume does not move with the fluid. If a control volume moves with the fluid and the boundaries are basically boundaries drawn by particles that moves with the fluid, then it's called a Lagrangian control volume. So this is not that case. This is a fixed control volume that's stationary relative to the airfoil we're looking at. It doesn't change as time goes on. So in this control volume, and let's assume everything has achieved a steady state, so that basically if you fix any point in space relative to the airfoil, the velocity and the pressure and everything doesn't change, right? So that's typically what we are looking at when an airplane is flying at a steady speed at a fixed angle of attack, right? So the flow doesn't change as a function of time. So basically, we are assuming the partial u, which is the x velocity, right? So let's say the velocity at any point is u as a function of x and y in the x direction. And the velocity in the y direction is v as a function of x and y. Okay, so partial u, partial x is equal to 0, and the partial u, partial y, sorry. That's not what we mean. Partial u, partial t is equal to 0, and partial v, partial t is equal to 0. So the time derivative is equal to 0. Now let's stop a little bit and make sure that we understand what we mean in this scenario by partial derivatives. Okay, what is the difference between like a total derivative and partial derivative? If you're rusty about multivariate calculus, this is a good point to remind ourselves because we're going to be using this a lot. A partial derivative operates on a multivariate function, like in this case. So let me just make it more explicit and write it in the general case of u and v as a function of x and y and t. Saying that the partial derivatives are equal to 0 means that if you fix all the other variables and only changing t, that rate of change is equal to 0. That means if I fix x, fix y, and only vary t, the rate of change as I vary t and fixing x and y equal to 0. So if I have these, it's called a steady state, a steady flow. So if I have steady flow, then I can really get rid of the variable t in this equation because my flow field does not change as a function of t, right? Okay, so if we are assuming, if we are fixing a Eulerian control volume and assuming steady flow, then let's write down what the mass conservation equation is. If you remember what we studied in Unified, the mass conservation equation looks like this. The time derivative of the total integral, in this case, let me write two integral as an integral within this volume, right? So if I integrate within this volume, it's a integration in 2 dimensions. And let's say this control volume, let's make it omega. So let's say omega is the control volume itself. And if I write down the density of and dx dy, right? So this is how much mass do I have in this control volume. And if the flow field doesn't change as a function of time, then I know that this derivative has to be 0, right? Because my flow field is not changing and my control volume is not changing. So the mass inside it cannot be changing. All right. And that time derivative by the conservation of mass has to equal to the amount of mass that flows into the control volume minus the mass flows out of the control volume. And this inflow and outflow can be represented as an integral on the boundary of the control volume. So let's actually denote this boundary as partial omega, right? Omega is the interior, and the partial omega, it's a mathematical notation for the boundary of the control volume that is has nothing to do with the partial derivatives, okay? So it is equal to integration over the boundary of the normal, and the normal always point outwards, right? So that's the normal, that's the normal. Okay, so the normal times the velocity as a vector. So the x component is small u and the y component is small v, right? And we also multiply density over here times ds. And ds is a small element on the boundary of this control volume. So this is the kind of a mass conservation we started in Unified. And let's specialize in this case and try to drill down this mass conservation into something that actually doesn't just work for a control volume, but for every point in the flow field. Because now, as we are getting to predicting the lift of an airfoil quantitatively, we don't just want to look at the whole airfoil as a single thing, but we want to look at every point in the control volume. We want to know everything that happens everywhere in the flow field. Right, so let's actually look at this control volume as a square and look at the limit case as we make this square smaller and smaller and smaller and see what we get. And now let's start at this general form of the mass conservation and look at what this means for a control volume that is a square, and then take the square to a point, shrink it to a point. Okay, so now let's look at the left-hand side. We know left-hand side is 0, right? So for this special case of steady state flow field, the left-hand side is 0, and the right-hand side is an integration over the 4 sides of the square. Let's look at the 4 sides one by one, okay? And let's also assume that because we are looking at a incompressible flow field, right? We assume our density is a constant. A density being a constant is nice because we can then pull the rho out of the integral.